I am heading the research area networks at Ericsson Research. Together with my colleagues in radio, compute, AI, security, and our other research areas, we make up the core of Ericsson's most forward-looking unit. It's therefore my pleasure to spend some of your time today talking about the future, that is 6G, and some of the journeys that we as a research community can take to get there. Now, I was very much looking forward to being with you in person at the 6G Wireless Summit in Levi to talk to you and hopefully argue with you. I feel that research is about exploring and charting new territories, which is, I think, best done through recent analysis, of course, and then with feedback and interaction among peers in our very strong international academic and industrial research community. However, the situation with the ongoing and increasing spread of the new coronavirus in many countries, in particular right now in Europe, is very serious. And like many other organizations, Ericsson has taken steps to protect both our employees and the communities we interact with through restrictions on travel and event participation. And now we also see countries and local communities around the world enforcing measures to limit social interaction, and by that, hopefully the continued spread of the virus. Arranging a conference like the 6G Wireless Summit in these times is for sure very challenging and difficult to plan. The easiest thing would have been to simply cancel the event entirely. So I therefore much appreciate the tremendous efforts of the organizers to still run the summit and adapt it to a fully virtual event. This can't have been easy to do in the short amount of time that was available. So I'm grateful for the opportunity to provide this recorded presentation. Of course, a great disadvantage of being recorded like this is that we cannot interact during the talk, but I want to hear what you think and listen to your input and questions anyway. This could be an online Q&A session or some other interactive session now at the virtual summit, or anytime later. You can contact me or anyone else of us at Ericsson Research to discuss the future. This is a topic that we are really interested in and want to do research on together with you. So, I've used the word journey now a couple of times, and I will use it a few times more. It's a good word. It captures a sense of direction and a way forward. Journey usually also starts somewhere and ends somewhere. Now, it's difficult to predict the end point of a journey into the future, and even more so when it lies in the distant future. However, thinking about the future can help us to create a map of things to explore. And if we also go ahead and explore many of these journeys, the chance of getting onto the right track will for sure increase. Our journey here starts with 5G. From research, we started a long time ago on 5G, at least as early as in 2012. And for some technology components, we can trace back our research work even earlier. So last year, we saw the first 5G networks being switched on. And by the end of 2019, approximately 8% of operators had launched live 5G networks. The focus was clearly on consumers. Now these networks are with restricted coverage, focusing on cities and populated or very highly populated areas. At the end of 2019, there were 13 million 5G subscriptions globally. Service providers launched non-standalone 5G in one selected frequency band, and the use cases were primarily smartphone driven. What do we expect of this year? Well, we will see 5G scale up. And in the Ericsson Mobility Report, we estimate that there will be close to 100 million 5G subscriptions globally by the end of the year. And a big share will come from China. Volume devices and mid-tier smartphones will be introduced. Hopefully the price could go as low as $300. There will be wide 5G coverage by a few early movers, and 5G will be launched by perhaps 20 to 25% of LTE operators. Enhanced mobile broadband and fixed wireless access continue to prevail for consumers. Trials will continue on 5G for industries, and we will see many deployments still happening on 4G. Standalone 5G will be introduced this year, which will for sure bring better experience, more innovation and network slicing. Service provider will also introduce 5G in multiple bands. And currently Ericsson is supporting now 26 live 5G networks across 4 continents. All those networks use Ericsson Radio, Ericsson Core, or both. Now, as a key innovator in mobile systems, and with a, as you see, strong market position, we hope to bring our ideas and insights into the 6G research period that we see now ahead of us. So we talked about how in 2020 we'll see continued trials on 5G for industries. And I wanted to bring an example of how 5G can transform enterprises and businesses to enable new use cases. And this is about vehicular communications, where our roads are becoming an overwhelmingly complex connectivity ecosystem with lots of new overlapping cloud platforms and vehicles connecting to each other, to cyclists, to pedestrian and other vulnerable road users, and to the road and signaling infrastructure. Cellular vehicle-to-everything connectivity will enhance advanced driver assistance systems, providing information on upcoming signals, traffic and accident situations. So here's a trial which was done last year by Ericsson, Telecom Italia and Audi in conjunction with the 5G Automotive Association. And it used 5G to pioneer an IoT-powered advanced driver assistance systems initiative in Turin, in Italy. So several use cases were included in the trial. The one we see here shows aquaplaning with intelligent tires and infotainment AR via a live 5G network. So we have a number of cars here in the trial. We see a first car detecting a dangerous aquaplaning situation through the tire sensors. And then the onboard computer transmits to a 5G connected cloud. Live 5G network processes data and relays the information to other nearby cars. Safety information is then presented to the driver through augmented reality, and then the dangerous situation can be avoided by controlling direction and speed. So, as you can see, these advanced driver assistance systems can be provided with 5G systems today, and further vehicle connectivity use cases will be enabled as 5G continues to evolve. So starting from 5G, we're now ready to talk about journeys that can be taken towards 6G. Since 6G lies quite far into the future, it is very difficult to know where we will end up. Nevertheless, we have spent some effort now to map different technology drivers that we think will be important. We have also tried to sort them a bit into a map of potential technology journeys that we see ahead. So, technology journeys. I mean, some of the components that you will see here may evolve over time, one after the other, and some may depend on each other, and some may emerge when advances in different technical domains are combined in new ways, leading to perhaps completely new technologies and capabilities. And this last possibility is perhaps what excites me the most, and it's this potential combination effect of different technology domains that can create new communication possibilities. So let us now quickly look at some of these potential journeys and the stepping stones along the way. So if we begin from the top there, we have the Internet of Senses. And in the Internet of Senses, visual, audio, and haptic and other technologies will allow human beings to have remote sensory experiences close to the ones experienced when executing actions locally, and also to interact seamlessly with remote devices and robots. Starting from some enablers for XR already now, the network needs to support these services streaming from the cloud, and low-weight AR glasses emerging will need compute to be pushed to the network edge. There will be need for many technological advances in devices and sensors. And for holographic communications, we might see the emergence of 3D light field displays as a new media type for 6G, replacing very demanding requirements on the network. Moving on, we will see a number of body augmentation capabilities that will enable humans to be smarter, stronger, and more capable. This could be contact lenses that can take pictures or shoot video, universal translator earbuds, exosuits, and all kinds of different implants. And finally, then brain-computer interfaces that are wearable and implantable are already today being in development, and in the future they could lead to quite dramatic changes in how we communicate with each other and how we interact with digital devices. Next, connected intelligent machines. So traffic in mobile networks might in the future be dominated by connected intelligent machines. and AIs that are communicating directly with each other. And this may have implications on how we should design mobile networks, which in this case are not limited by the capabilities of human senses. There may be their own way of perceiving data or information, so requiring us to define new data formats, for example, new types of video compression mechanisms. Semantics and how machines communicate and interpret data will also be very important. The network itself could also be viewed as an intelligent machine serving other intelligent machines. For example, with network exposure capabilities, compute and data hosting and features for data handling. And if we draw this line further, we may arrive at a system of systems created when connecting intelligent machines and the future network are together interlinked, and where we see joint pooling of resources and capabilities to provide functionality, performance, and intelligence that go way beyond the sum of these individual systems. Next, in 2030, we feel we will live in a fully digitalized, automated, and programmable physical world. And technologies for this, of course, positioning and increasing high precision positioning will be very important. And here we see the high frequencies used in 5G evolution 6G will translate to shorter wavelengths, which of course allow then better resolution, perhaps up to centimeter precision in localization. Sensor fusion will be necessary to create an accurate digital representation of the physical world by fusing information from many sources, including network data. Digital twins, already today used with industrial machines. In the future, every physical object that would benefit from a digital twin would probably have one, and leading to a pervasive cyber-physical system. And moving forward, we will see digital twins start to be interconnected and collaborative, so we can create representations of even larger entities. For example, if we have a digital twin of all objects in a smart city, we could create a real-time digital representation of that entire city. And then when these are all fused together and interconnected digital twins and also digital representation of the environment, which we might be able to get through a joint communication and sensing system, we could essentially get a digital representation of everything. And that would allow us to create the physical world more or less fully programmable and automated. Sustainable world, mobile networks and ICT will continue to play a crucial role in accelerating progress towards the UN Sustainable Development Goals. Starting from the energy efficiency, we have of course already 5G and are increasing energy efficiency through technologies such as advanced sleep modes and reduced always-on signaling transmissions. 6G will need to continue to push overall network and system level energy efficiency. We have networks that will be increasingly powered with renewable energy. Alternative energy sources gain further importance. Operators already today committed to increasing the use, and we see many solar-powered base stations already in operation. Mobile networks help to avoid emissions by providing connectivity, efficiency gains, and change in behavior. And digital technologies will support using less materials in the economy and the society, and thus drive a smaller footprint on our planet. Finally, ICT, especially mobile broadband, will be an essential infrastructure platform for the Sustainable Development Goals. So while these are now 4 more use case focused technology drivers, we also have a number which are more technology driven. So non-limiting connectivity, this one we will elaborate a bit more shortly. It is about providing connectivity for all applications, allowing anyone and anything that benefits from being connected to connect anywhere at any time. Trustworthy systems. 5G evolution and 6G will increase the trustworthiness of mobile networks to a level where the requirements of even the most mission and business critical applications are fulfilled. Secure identities are needed here to protect communication at every layer in 5G and for IoT. Flexible identity management, mechanisms for bootstrapping, trusted identities and credentials, and new transport layer security protocols are things that need to be researched. Extreme network reliability, availability, and resilience needed for mission-critical use cases. Confidential computing encrypts workloads while they're being processed using a trusted execution environment or enclaves. Hardware-based security, trusted computing, and secure enclaves will form the base for building security in future networks, especially in the virtualized and distributed system environment. And finally, integrated assurance of trustworthy operations. Very important, operators need to show that the networks are both secure and reliable. In the future mobile network, all operational processes and tasks will be executed with basically 100% automation. Network will become cognitive, continuously self-learning at scale from its experience and observations. So we'll see AI agents for multiple network functions, including optimization of the radio interface and automation of network management and orchestration. Closed-loop automation will remove humans from the actuation loop. Humans will, of course, then still interact with the network and monitor its behavior by means of intent-based interaction. The cognitive network will require AI and machine learning that is distributed and capable of acting in real time. Central AI and distributed AI functions will then use both local and global information and insights and data. And then we will be able to use federated learning to train algorithms across multiple network nodes. Finally, trustworthy AI is essential then for AI to run the cognitive network. And then our final technology journey here is about the network compute fabric. And here we feel that everything that can be viewed as a single unified integrated execution environment for distributed applications. And here we include both network functions and third-party applications. First step here is, of course, to make the network itself cloud native. This includes a cloud native core already happening, but also cloud native RAN using technologies such as containers and microservices. Hardware acceleration will be needed for radio access network workloads that have very high requirements on processing and timing. Serverless deployments may be used to make the system even more lightweight and scale more easily. And in the network assisted edge cloud, we will see network information exposed to and integrated with the cloud, either an operator provided cloud or the cloud of a hyperscale public cloud provider. And finally, future computing paradigms need to be researched and studied, and this could be quantum, neuromorphic, memory-centric computing, and many other sort of new compute domains. Now, the order and grouping between the technologies that we've looked at here, and it's just an example. I mean, some of these components may be closer to the current evolution path of 5G, including the 3GPP standardization in the upcoming release 17 work, while some may lie further into the future. We can guess now which are close and which are further ahead, but we can't be sure. And when the time is right for a particular technology component to be industrialized, I mean, we will bring it to the mobile system evolution path. I mean, it's either part of the 5G evolution or as a piece in the future 6G system. And again, just want to emphasize that this is not a system view or an attempt to scope 6G. It's simply too early for anything like that. It's a way to create a draft map of research challenges that will be important going forward. We can select any one of these technology components and in any order to do research on. So let us now quickly return to the non-limiting connectivity journey that we didn't discuss so much, from a little bit of a different angle and cover it in a bit more detail. So connectivity everywhere. So in today's 5G system, the network connectivity is extended beyond the 4G systems based on, for example, dual connectivity, integrated access backhaul, and a split RAN architecture. For dual connectivity, the wireless device connects to one base station, for instance at low frequency, which provides robustness by delivering the control signaling and some data signaling. On top of this, the device also connects to a second base station at a much higher frequency with much larger bandwidth. Since the high frequency may provide much higher throughput but with less coverage and can be more easily be blocked. The low frequency can be used for resilience, while the higher frequencies are used for capacity. This enables a gradual deployment of high frequency NR without the drawback of coverage holes. For integrated access backhaul, the large bandwidth of the high frequencies available for 5G are utilized for both access and backhaul. For this, an IAB node will act as a wireless device and connect to a normal base station. A normal device can then connect to the IEB node as it would to any other base station, and the IEB would relay the traffic between the wireless device and the base station, using the same spectrum on both links. This means that the 5G capacity can be extended without the need to deploy high-capacity fiber connectivity to all base stations, which enables simple deployments on, for example, light poles. For a split RAN architecture, a logical base station, a GNB, is split into two separate physical entities, one higher layer in a central unit and one lower layer in a distributed unit. The central unit handles, for instance, mobility, security, and connectivity to the core network, while the distributed unit handles scheduling, radio link monitoring, and physical layer aspects. Since the security is handled centrally, a device can quickly switch between different distributed units connected to the same central unit without the need to interrupt communication to update security keys, as would be necessary at the normal handover. So, in the coming evolution now of 5G, these concepts are likely to be extended to enable even further coverage and reach of high-capacity connectivity in cost-efficient ways. This includes, for example, non-terrestrial networks that are currently studied in 3GPP, mesh networks, and multi-hop IAV, where the traffic is routed even further away from the nearest fixed connection. And this also includes deployments of much cheaper base stations, such as the radio stripes that we demonstrated at the Mobile World Congress last year, which allows much more rapid and flexible network deployments. For 6G, these different technology components will be fully integrated into the network architecture, which will allow smooth transmissions between the accesses, utilizing the momentarily most optimal paths to provide the required services, for instance in terms of throughput, latency, or reliability. Next, joint communication and sensing. So current 5G systems allow data up to many gigabit per second per link using frequencies up to 39 GHz over very large bandwidths. In addition, NR base stations can broadcast specific positioning reference signals, which the wireless devices can use to determine its own position. These signals can also be used to measure distances to reflecting surfaces or walls by comparing the angle of arrival and observed time difference of arrival of the line of sight signal to that of the reflected signal. In the coming evolution of 5G, the maximum carrier frequencies will be extended up to 100 GHz, allowing even larger bandwidth and throughput. These higher frequencies also translate to shorter wavelengths, which allow better resolution, and the larger bandwidths can be utilized to increase the temporal resolution. So overall, this allows up to centimeter precision in localization that can be used to map the surrounding infrastructure and detect obstacles. For 6G, research is exploring even higher frequencies, realistically up to 300 GHz, which will further enhance the spatial and temporal resolution of the signal. So by integrating the positioning and sensing capabilities directly in the radio access technology, positioning information can be employed to enhance the connectivity, with, for instance, radio link quality prediction. Alternatively, the distance information to reflecting surfaces could be employed as an integrated radar for obstacle detection, for example in V2X application. In addition, these very high frequencies have distinct atmospheric and material properties, which have been shown to be sufficient to forecast weather based on, for example, air humidity. So, third, zero cost, zero energy devices. So, to facilitate the mass deployment of IoT devices, such as sensors and simple actuators, 4G was extended with LTE-M and Narrowband IoT to allow simpler wireless devices that only support a very limited bandwidth with long battery life. With the introduction of NR, with the initial focus of supporting enhanced throughput, the IoT use cases were down prioritized in the first two releases. However, in the now upcoming release 17, NR reduced capabilities, NR RedCap, will be studied, which will target the massive industrial wireless sensor networks, which have moderate performance requirements but are much more cost sensitive compared to the enhanced mobile broadband and URL LLC devices. And in the 6G area, the need for sensors and devices will be further pronounced, and they will be embedded everywhere. Even with the battery life of 5G IoT devices, the batteries will eventually run out, requiring costly replacements. So for 6G research, we envision low complexity wireless devices acting as sensors and actuators, which can be powered, for example, with ambient energy sources, such as solar, temperature variations, or vibrations. Alternatively, the incoming radio signals are used to power the device, similar to passive RFID tags and NFC devices. So by designing dedicated beamform power supply signals, the zero-energy devices could harvest sufficient energy to perform the task and transmit the signal back. In addition, the advent of printed electronics allows significantly reduced cost for embedding simple wireless devices into nearly everything, such as food packages, mailing boxes, clothes, wallpaper, you name it. Finally, artificially intelligent air interface. So AI is already today being tested and used throughout our 5G systems to enhance performance by predicting the future. This allows replacing rule of thumb configurations with dynamic optimizations, for instance, for mobility handling, secondary cell selection, or traffic prediction. So in the coming evolution of 5G, this AI optimization will be extended to span several parts of the network. AI agents in one part of the network cooperating or negotiating with AI agents in other parts of the network, potentially using federated learning, and where input data can be shared throughout the network. Perhaps the ultimate goal of machine learning in communications is to deploy air interface without any assumption on the channel or used models, and let the AI agent optimize the communication without any prior knowledge. For instance, in the artificially intelligent air interface, the AI agent is deployed ad hoc at a random location and can deduce by itself the optimal configuration to communicate with the network. It's also envisioned that network and device programmability will enable the AI agents to dynamically optimize the communication. So as a short example of how this could work, you will now see and hear a video of a self-learning air interface where the transmitter slowly converges to the optimal transmission pattern. Yeah, this is just a simple example and likely not how a real system would be implemented. Still, it demonstrates the opportunities for new approaches to some of the fundamental problems of wireless communication. So, we have looked at a number of different technology journeys that will develop over time. And here we see a timeline. We see the broad evolution of mobile system technologies in the middle, starting from initial 5G and now the ongoing ramp up of 5G deployments. Foundations for these systems is the global 3GPP ecosystem of standards, starting with release 15 baseline now for 5G and evolving with the now finalizing release 16 specifications and the startup of release 17 efforts. It is now time to start early research on 6G technology components. We expect that we need to spend several years of research effort in investigating them. At this stage, there should be an advantage to run many research projects that are spread across our community, as many as possible. At some point, there will be a need to structure and frame these technology components, and perhaps in the 2023 timeframe or so, to start broader systemization research projects, where we can bring in the findings of the earlier research efforts. In parallel, the work on spectrum for evolved 5G systems and 6G will be addressed towards the World Radio Conferences in 2023 and 2027, and work will also start to define 6G requirements for later use in systemization research and standardization in 3GPP. Moving forward, we may see 6G systems being commercialized and deployed in the 2030 timeframe, or perhaps sooner. So we have identified 8 potential technology drivers for the future that possibly could lead to 6G. And right now it's really not possible to predict how strong each of these drivers will shape the definition of the 6G systems. But we believe that 6G in one way or another will be a combination of all these drivers, and possibly more. So this concludes my presentation. So we are at an exciting time to start research efforts on 6G technology components across a wide range of technology domains. Our journey towards 6G is just beginning. Finally, let us all take care and support each other and all of our local communities now in getting past this current situation with the coronavirus. We can take lead in this using our own digital technologies to keep focus and drive technology and research forward. Thank you for listening, and thanks again for the organizers of the 60 Wireless Summit for persevering in making this event happen. Thank you.